starting.
All right, so Jonathan, shall we get things started?
Yes, please go ahead.
All right, so it's a great pleasure to introduce Arthur Adams. So Arthur is, I would say, just really excellent researchers in exoplanet, has done a wide range of interesting projects. I think that's reflected in the title of his talk. Arthur is going to talk to us about the cascade of dichotomy in planet formation and evolution. I want to highlight that Arthur is going to join us at UVA, I think, as well as Vico at the beginning of August. So I hope to use this opportunity to let everybody to welcome Arthur to join us. But then I'll just give the floor to Arthur and let you to tell us about all this exciting science that we've been doing over the years.
Yeah, thanks, Yifan. And I will say that this talk will focus on one of the major projects that I've been working on the past several years. Just, for the interest of time and I guess clarity, but given that this was, as I understand it, a 30-minute talk followed by a 30-minute discussion, I was thinking about the ways in which I could frame a science talk in terms of a broader discussion. And so I relied on kind of, the experience that I have built in planet characterization, through planetary atmospheres, to kind of think of an interesting way that I've seen recently to frame how we look at atmospheric or planet characterization in general. I haven't decided whether this is the first time I've used this title. I haven't decided whether it's too pretentious or not, so I'm happy to get feedback in that regard. So this title will be kind of the bigger picture discussion, and it will be kind of a wrapper around what is otherwise my science talk, which will be familiar to Yifan. This is the work that I've been doing to characterize planetary mass companions through direct imaging. So kind of the outline of this talk is I'll just give you an introduction to one of the objects that I've worked on. This is kind of an icebreaker, and then I will kind of say how I think that the discussion could go. And we're welcome to take the discussion whatever direction you want, whether you want to focus on this particular science or any of the questions I raised, or it's up to I guess it's up to the group. And then I'll bring it back to the larger picture at the end after I go through the specific science. So I like to start with a picture, and this is the HD 106-906 system. So this is in the Upper SCO Sen Association, if that means something to you. What's interesting about it is that it has a planetary mass companion. So from evolutionary models and fitting the spectrum, this is stuff that was done before I worked on it. The inferred mass is right near the deuterium burning limit. And so one of the interesting questions was, does this object match more of our concept of what we think a planet is, or does it match something closer to a brown dwarf? So let's call it a substellar companion. And so when I use the term companion throughout this talk as just kind of a reflex, you should just think of an agnostic term to describe a smaller mass object orbiting a bona fide star, and it could be something that we could call a brown dwarf or a planet. It encompasses both. What's interesting also is that this is a very young system. So it's got we think that the age of the system is around 15 million years. This is a low gravity target. So for atmospheric characterization, that has implications about what spectral features you expect. And it is very widely separated. So that's kind of the actually main thing, is that you can see from this picture, it just gives you a sense of the scale. It is 7 arc seconds away from its host, so easily directly imaged. And that corresponds to, this one says 650. This is the original Vanessa Bailey paper from 2013. We think maybe it's more like 730 AU in projected separation. So very, very widely separated. So
what is the mass of the host star?
Good question. So the prevailing conclusion is that it is actually a binary, a very close binary, less than 1 AU, of 2 F dwarfs. So each of them has about a mass of 1.3 solar. Okay. So that would mean that the combined, I think, or maybe 1.2. So the combined mass is somewhere around 2.4, I think, solar masses. Mm-hmm. So it is a very interesting system in that regard as well. I'm happy to think about that as well in the discussion. So that's but this is the mental image that, I'd like to, or the physical image as well that I'd like to give to you. So the broadest way I can frame this is we're interested in how do planets form. Okay, that's we like to think about the biggest scientific question. And when I started this project, the research group that I joined, I was coming from a phase curve analysis with thermal phase curves of Spitzer. And so I joined a group that was very interested in the formation and evolution of planetary systems. And so while I was working on the atmospheric characterization, I was also getting more acquainted with these ideas of how, the demographics of systems evolve. How do we know, what do we know about how many planets form as a function of the mass? And as you'll see, we often talk about the mass ratio in the case of these companions. The orbital separation, given that this particular target is out at 700 AU, and a lot of our demographic studies have been done much closer to the planet host stars, and binarity as well, right? So good that Jonathan pointed out the binarity of the system, or any other distribution of existing planets. And so the way that I'll kind of talk about the formation is that at different mass scales, those are all going to have effects on what other distributions of mass scales form. How many large planets or gas giants are there certainly should have an effect on how many and at what orbital separations you form smaller planets, right? So that's what I kind of mean by that cascade, but I'll get into that idea. And then as from the atmospheric side, I'm certainly interested in what are the physical processes that will shape the sizes and states of those planets. And by sizes, I mean kind of mass and radius generally, and then states are the things that is it temperature, which could certainly be orbital separation, but also just the atmospheric composition, the density, and anything that goes into that. It's just a catch-all term. So for the broader discussion, before I get into the details of my analysis of that system, again, this is just the first time I've laid this out in a talk, but I kind of identified these three dichotomies that I've been exposed to. In this particular project, I think one of the main questions that comes up is, where do stars end and planets begin? And that, you could characterize that as a simple mass cutoff at 13 Jupiter masses, which is where we expect. Above that, you can fuse hydrogen into deuterium in the interiors. Below that, you don't. So that may be your definition of what separates these two classes of objects. But as I'll kind of discuss, an alternate, similar but distinct definition is about the way that they form. And so that kind of, there's this framing of that characterization effort as there are these two sides of the classification system, and it sits, is it a clear-cut definition? What do we mean by that? And as we learn more, how would that classification change? The second dichotomy that I kind of hear a lot about, and I've done a little bit of work in, but I won't have time to talk about today, is what determines which planets end up gas-dominated versus solid-dominated. So if you've heard about the planet radius gap or density gap, depending on who you talk to, there's an observed separation between objects that we believe are more gas-dominated, that they either retain or are able to have an extended hydrogen-helium envelope, like the giant planets in our solar system. And then on the other side of this radius gap, we see planets that are likely to not have that, and that introduces a significant difference in the radii that you can see in the distribution, at least from the planets that we have survey information from now. And then the last one that I think is the most important, and working in Stephen Kane's lab here at UC Riverside, he's very interested in the dichotomy of Earth versus Venus. So that I would say when you get down to the masses of Earth-like masses, terrestrial planets, that seems like the big question, right? Are Venus and Earth are certainly different today, and if you want to divide them by, say, habitability, however you define that, how do Earth and Venus end up so different? And are they two ends of a very clear-cut dichotomy where planets just either are habitable or not, or what are their histories and that sort of stuff? So I'll kind of bring us back to that. But getting back to this question, I'll start talking about this project. that starts to address the first part of those questions. So getting back to HD 106-906b, so B being the companion, there's been a lot of interest in this system, and so I'd like to highlight some of the characterization efforts outside of atmospheres. So Marta Bryan's paper in 2021 kind of gave us a really interesting and thorough characterization of the momentum and the dynamics of the system currently. So actually, that's the way it looks projected in the sky, so that you can compare these two figures. But essentially, she did the whole, was able to constrain not only the orientation of the planets or the companions' orbit relative to the debris disk that still remains, given that this is a 15 million year system, but also had a constraint on the planetary obliquity. So this is a wonderful just result, and further kind of adds evidence to the possible, well, I'm not saying it's conclusive at this point. I think it's, we have ideas, but they're, gives you a lot of evidence to work with in favor of one, formation hypothesis or another. And then this Moon paper from the same year gave a really good orbital characterization, and so I really like this figure. So if you project this onto the Vanessa Bailey original publication, she's the one who published the object initially. That's about the scale that you're looking at. More recent paper, Moore et al. I think Nathaniel Moore, forgive me, I know you're not here, but if I get your name wrong, recently looked at the idea that the companion could be the result of a close encounter with a foreign object to the system. And so actually the possibilities that he raises in that are either that a flyby induced a initially close-in orbit to a eccentric large orbital separation, or that there was an exchange, and that actually HD 106-906b is has a origin outside of the original system. So I don't have any words on that. It's just very interesting, and so there's a lot of active study in this system. The thing that I got introduced to when I started this work is the idea of using the mass ratio of the companion to the primary, in this case the binary, and using that to infer something about the demographics. So if you talk to Michael Meyer, who was the original, so was my kind of supervisor at University of Michigan when I started doing this work, he'll tell you that that's the kind of core parameter that you want to be using. And these are this is a slide I adapted from an old talk, but I'm sure that the point remains that regardless of detection technique and demographic survey from either microlensing, imaging, or what have you, that there seems to be a minimum in the distribution of these companions at a mass ratio around, so log 10 here minus 2, so about 1%. Now, HD 106-906b kind of sits a little bit smaller than that. It's about 0.5% or so, roughly. So it is an interesting, it sits in that thing, that mutual minimum between these two distributions, if you want to break them up. And so that warrants its investigation from that perspective as well. So the dichotomy that I mentioned earlier is that the companions could form like planets or stars. So I alluded to the mass cutoff as a distinction between these two classes of objects. But from a planet formation perspective, there is a parallel definition of, does it form in the context of an existing protoplanetary disk, acquire its solids and gases through orbiting and evolving and acquiring its material in that form, whether it's a core accretion model, you believe that, or a disk instability, right? So these are the two main models that people refer to. Or is it forming in the way that a stellar binary would, or I guess in this case a ternary system, where you collapse from an initial fragment of a molecular cloud and then dynamically evolve into a gravitationally bound system. I should point out that it's rare. It's difficult to get an object of this mass, or at least as inferred mass of this wide of a separation, regardless of which pathway you believe is more likely. So this is a rare object, right? There's only a couple of these objects that we know of currently. But the main hypothesis, kind of the distinguishing line that we set out in this project, was that the carbon to oxygen ratio should tell you something about the formation pathway. And as I'll describe, it's certainly not the complete picture, but that was kind of the main thing that we wanted to test in the initial project. So this is the main results of our atmospheric retrieval. So I am not going to go into a lot of detail about the code that we use, but I'm happy to answer questions about what approaches we use, and I'll provide a couple of details sprinkled in as I show you these results. But I should say Alex Howe was the original creator of the code, the Apollo code that we use, and I've been adapting it over the past couple of years to retrieve on these objects. So again, if you're not in the atmospheric community, we use retrieval just to say, generate a model and fit it to data. So I don't know why we use retrieval, just it sounds cool. So what you're looking at is a binned spectrum that we got from the ground. So this is a J, H, and K, so near infrared spectrum at a resolution from about 2000 to 4000. Signal to noise is probably about 20 here, and it represented kind of a, the best spectrum that you can get of these directly imaged companions from the ground. So you get all the advantages of the resolution and the aperture and all that sort of stuff. So what we were hoping to do is, again, to constrain the carbon to oxygen ratio in the midst of all the other atmospheric characterization that one would need to do in order to properly constrain the structure and composition of the atmosphere. So what I highlight here is the fact that and this represents several years of effort to get what we considered an appropriate fit for the data. It was a challenging effort, and if you ask anybody else in the L dwarf, which is the spectral type here, they might allude to similar stories of difficulties in fitting this sorts of objects. That we were able to get a good fit, and here I'm showing a difference between a cloudy and a clear model. So that is just whether we account for opacity due to clouds in any form. This was an intentionally simple cloud opacity model, and so without going into a bunch of details, it's an empirical, just kind of wavelength dependent model. And we're not modeling any specific particles. We just said, okay, there's some opacity that has some linear dependence in optical depth, and our model puts the cloud up here in the atmosphere at about, so on this scale, 1/100th to a millibar to 10 millibars or so. Again, I'm glossing over the details of this, but here we get a good fit. We have these temperature pressure profiles that we retrieve for both the cloud-free and the cloudy model. And then the thing that we actually wanted to constrain, I show here in this histogram, there are many other parameters, but one thing you can pull out is the carbon to oxygen ratio for the gas content in the atmosphere. And one thing that I haven't mentioned is that you get a CETO ratio constraint, but you need to compare it with the CETO ratio of the primary, because that dissimilarity or similarity is going to tell you hopefully something, lend evidence in favor of one formation pathway or the other. This constraint of 0.53 for the cloudy model is close to solar, and so in this paper we said there's no reason to rule out a binary formation like a substellar companion versus a planet. And so we did the arguments of why we believe that the association that this belongs to is should have a close to solar CETO ratio. But I'm happy to answer questions about any of this. As a part of doing this constraint, so that was the goal of this paper. But you may notice if you study any of these temperature pressure profiles that the structure of this vertical profile is odd compared with something that you would get from a radiative convective model, right? So what I'm showing here in this kind of chocolate bar line, I guess if you want to call it, is a Sonora model from Mark Marley et al. So they made all these cloud-free radiative convective equilibrium temperature pressure profiles for objects across these temperatures and gravities. And so we fit it to the retrieved gravity and temperature or a similar object, and you get something that looks quite different. And so one question we had that we didn't answer in the paper is, and still really haven't, is why do we get temperature pressure profiles that say are a lot more, are closer to isothermal up to about a pressure of a bar or several bars, and then kind of, then show some structure. One thing that I wanted to also highlight in this is that this was not just the retrieval on HC 106-906b, but that it was there was a lot of effort that went into testing the model and comparing with these sorts of objects. So as part of this, we did what I'd call an asynchronous comparative retrieval. That is, there was already a paper out on another L dwarf. This is a field L dwarf, so high gravity, of this 2-mass target from Ben Birmingham et al. In 2017. I should point out that they recharacterized the system in 2021, but I'm just comparing the same wavelength range that we used, which is their original paper. And what was interesting about this is that we do, if you see my cursor, the CEDO ratio that we retrieve is quite similar, although we do get a different, we disagree on some very fundamental parameters of the system, right? In particular, one thing that we found was that the log G, the surface gravity, was very high. Now, this object may have a surface gravity log G of around 5. That would be expected for a field dwarf. 6 may be a little too high. And so the inferred mass you see here is very large. In fact, it's stellar. So I don't put any weight into that. I'm just, our model retrieves a very high gravity, and that will lead you to infer that if you trust that that is the correct gravity. The answer that we think is that the gravity is not actually that high. It's just that we don't have enough information to constrain the temperature profile. But regardless, so this will be highlighting that we're doing this comparative retrieval. We get similar answers for the metric that we are concerned about, the CEDO ratio, but there is something about these data sets that, at least for our model, yield something that we consider is probably infeasible, like this infeasibly high surface gravity. And so that may just be an artifact of what we can constrain from the data we have. One more that I'll highlight, I realize it's getting a little bit late in time. Maybe I will just kind of highlight that we're working on this other target, and we're doing another comparison, this time in-house at University of Michigan. I'm working with the folks there still. So Ryan McDonald, who is a Sagan fellow there, has his own code that he usually applies to transmission spectra. And I'll just say that we're doing work to do a simultaneous comparative retrieval with both our codes. And we do still get these TP profiles, temperature pressure profiles, that are quite close to isothermal. That is, they'll look, have this high slope and stay, this is, again, not what you expect from a radioconvective equilibrium or any answer model. So the fact that we both of our codes get this answer is interesting and warrants, further investigation, right? Because I think this is something more to do with the model, what the data can tell us versus what is actually going on in the atmospheres. Okay, so I'm going to break here and go back to the bigger picture. So what do we need to learn about how planets form? And so from an atmospheric modeling perspective, what I'm most interested in is where are the atmospheric signals that tell you something about different structures and compositions in the data? What are going to be most informative, right? So maybe the near infrared, actually we kind of know that the near infrared alone doesn't give you the whole picture. So JWST is already proving that we can get a lot better constraints when you move out longer wavelengths. So this is just saying which of our current assumptions, which of the simplifications in our models need to be revisited. So again, these are ideas that are not unique to our subfield. And also I highlighted that the CEDO ratio is just one number. And anybody who works in this field will tell you that there are a wealth of different atmospheric tracers, even just in the case of characterization, that could tell you something about how and where in the protoplanetary disks these objects are forming. Are they forming interior, exterior to a certain ice line? How do they move through that, and then subsequent evolution over time? So this is not to show you any specific details in this table. This is to show you that there are many other things to look at besides the single number, the CEDO ratio. That was just the starting point. When we look at JWST spectrum, we get this wonderful wealth of data and just unprecedented resolution across this whole wavelength range. So I just wanted to highlight, in the past, we would rely on ground-based data here in the near infrared, and then maybe a Spitzer spectrum, IRS, that is a low resolution spectrum out here, and then you could span a similar wavelength range. And nothing wrong with this Johanna Voss paper. I actually think she did a great job, but just to highlight how much we learn when we move to JWST and the space observations from space. So Brittany Miles's paper is just kind of the groundbreaking paper and these sorts of targets, right? Directly image companions. I don't have a lot of time to go into the variability, but I'm sure if you're at University of Virginia and you talk to Yifan or any of his research group and colleagues, you hear about variability being the next big question. So maybe I don't mean to gloss over your work, Yifan, but just to say that this is a next question of study, and variability across different levels of 1% to even 30% in the case of the target that Brittany Miles published on is just an outstanding question that we're very interested in modeling, right? Because that's going to give you you're going to have to account for not just a single model, but how that varies in time and what observations you're getting from that. And then this is just a pretty collage of figures from others, just showing the different ways that we might expect that variability could arise in these objects, these L's and T dwarfs. And so, clouds, evolution of cloud or dynamics in clouds, star spot-like features on these objects, and how the objects rotate. You can imagine the combination of those could give you any number of structures that could introduce variability. So these are the ideas that we're looking at. But again, that'll be stuff that I'm working on and helping Yifan with when I come to University of Virginia. So maybe I'll just kind of leave that there. And I'll bring us to the takeaways of the science talk, which is the biggest thing that I've learned as I've gone along is that you learn more about what you need for your atmospheric models as you go along. It's always an iterative process. Again, nothing unique to our subfield, but it's just kind of going through this and having this experience with kind of a new developing field of atmospheric characterization for exoplanets. Kind of really highlights how much we don't know, but how much we'll get in the future. And, we're very helpful. Comparative retrievals, nothing unique to our group as well, but they are becoming the new norm. And so one of the cuisines working groups, I won't go into a lot of detail here, but just to say that that's a big working group with JWST data. And so they're starting a new working group for comparative retrievals. If you're in this field and you're interested in kind of getting a part of that in the JWST era. And then just saying that our models need to adapt to new data, and we're also interested in variability. Okay, so now I have one more slide of actual text, and then I'll bring it back to the discussion that we might have. Again, this is just a wrapper around the science talk. You're welcome to ask questions or talk about any part of it, whether you want to focus on one or the other. But for the discussion, I thought of this idea that we revise our science questions and framing. In this case, as we learn more about planets through their atmospheres. So there's many things that we can't get through the atmosphere, or at least can't yet get, which is how the interiors of these planets are structured, how that influences the atmospheres, the evolution of these systems through time. We're only observing them at one point in time. Many questions that will have some effect ultimately on the atmospheres. I'm going to also see parallels in the framing of this kind of planet versus brown dwarf, like one or the other, this dichotomy in the idea of super Earths versus sub-Neptunes in that Radius Valley example, and also the idea of when we move to say HWO, Habitable Worlds Observatory, and in our case, I've been thinking a lot about that in particular. The idea of exo-Earths versus exo-Venuses. Are we going to see this kind of, are we going to expect a dichotomy in the way that we see in the solar system, or as we might expect? I think we're going to see something that's quite a bit more diverse. And so how does that role of identifying these kind of separations into two classes, how will that evolve over time? So that's kind of the flavor of what I mean by this cascade of dichotomies, is that, I talked a lot about the first bullet point here, but I think the next kind of steps down the mass, the size scales also are framed in similar ways. And so maybe I'll just leave this here and we can move into a discussion. But thank you for your attention. I'm happy to answer any questions about the science as well.
Great, thank you very much. Okay, so we can now have either direct questions, or we can go to a discussion. So maybe if there are particular questions first about anything, I have lots, but we, raise your hands in Zoom or here.
Hi, nice talk. I just have a quick question about the CETO ratio. So what value do you expect for the case that the brown dwarf formed much further from the central stars, would it be lower or higher than what you're deriving with your modeling?
Yeah, so it's the answer is it depends. If you the leading theory, well, okay. So the answer is it really depends on when and where it forms in the system. So you know, we initially thought, oh, we would expect a low CETO ratio if it's acquiring a lot of like water or, you know, oxygen-rich material, and as it accretes like far out. And then you don't know whether another question is you don't know how the composition of the interior of the planet differs from the atmospheric composition. So I know I'm giving you kind of a non-committal answer, but the answer is it really, you know, there are diagrams from papers that'll show you how it could be higher, it could be lower, and it all depends on you know, how it evolves in the system. So we didn't have an a priori expectation of what it should be, other than just, you know, if it's consistent with the stellar CETO ratio, then we don't rule out the hypothesis. But if it's very different in either direction, then we would say, okay, it warrants further investigation with a more detailed consideration of how that evolutionary pathways would affect that. So,
can I follow up on the CETO ratio? You mentioned the primary stars they actually have a direct measurement of CETO from.
That's correct.
And what is that? Because I'm not sure I remember the number.
Oh, I'm sorry. Did you say so the primary does not have a directly measured CETO ratio. So in our paper, what we did, and actually this is a field of study as well, not a whole field, but an effort as well, is that can we get proper CETO ratios of the primaries? What we did for this paper is we kind of estimated it. So we don't get a very good precision on the CETO ratio, but it's essentially consistent with solar. I think it's like 0.58. In fact, I can go back to the slide where we looked at this. Okay, so here the red histogram here. It was something like 0.58 plus or minus 0.1, I think, or something of that scale. And what we did was we took the distribution of metallicities from the stellar association, and then we used a relation to map the metallicity to this variation metallicity to the variation in the CETO ratio. So it is just inferred, and that's why we have error bars of like 0.1. Yeah, it's an open, you know, that we actually do need proper, in most cases, proper constraints in the CETO ratios of those primaries.
So it's not really my area here, but I'm trying to remember stellar atmospheres. Is there any prospect for improving that CETO ratio in the primaries then?
Yeah, I've only considered it through my own atmospheric modeling. So my approach is, can I throw one of my atmospheric models and try to capture the structure of these primaries? And once they get above a certain effective temperature, then, you know, we just didn't have the readily available like opacity data to get that. But in principle, it should be doable. It's just, you know, I've only been thinking about it in the case of, can I approach that?
Mm-hmm. Okay. Well, then I was going to ask about the clouds. So when you have clouds, it looks like your errors on your CETO ratio are fairly large.
That's right.
So does that limit our ability to ever use the CETO ratio in this way to do a test?
I believe so. Given the limitations that I think the ground-based data yield, I don't think that it is. I think that the situation will improve when we move to JWST. And in fact, there's some folks who are doing atmospheric retrievals now who may have more precise constraints on CETO. But I think a lot of the discussion around this is what beyond the CETO ratio should we be looking for to paint a more comprehensive picture? Now, I think part of your question also referred to, do clouds limit our inference of the CETO ratio? And the answer is, originally, they were kind of a nuisance parameter, or a nuisance that we were hoping to constrain in order to get the atmospheric CETO ratio. But you can't really avoid them. So I think, people are doing their best to model them as just part of the atmosphere. They exist, and they also may have carbon and oxygen in their composition. So, moving beyond this sort of model, which others have, like, properly modeling the microphysics of clouds to whatever ability you can, whatever the data warrant, will be important, because then you can at least put an estimate on how much of the composition is affected by what's tied up in the condensates.
Okay, and any other questions now?
I guess about the ratios. Yeah, since we're talking about the ratios, are there any other, what's the next most diagnostic or useful elemental ratio, say beyond the C to O that you would want if you had a wish list?
Yeah, a lot of people in my group are talking about the nitrogen abundances. And, I actually won't claim to be an expert on exactly what like my rank order list is. I'm mostly interested in atmospheric, kind of the structure and modeling of atmospheres, but even metallicity as a whole is some tracer of it. But if you look at like the big, what was it, the big table that I flashed at everybody, I don't even know where it is. Sorry, as I do this, I'll say, yeah, so nitrogen, I think, is something that people are interested in, maybe the C to N ratio. A lot of these tracers here, for example, so you see like just the abundance in nitrogen. So in the object that we're modeling currently, we don't see a lot of ammonia, which is interesting because, at least from a chemical equilibrium standpoint, for that effective temperature, we might expect more. So I have no good follow-up for that. I haven't interpreted it well enough yet, but I would say probably nitrogen is probably the next element to look at.
And how well can you measure metallicity?
Yeah, I don't want to. I have so few good conclusive questions for the group.
The retrieval would return a value of metallicity.
That's correct. That's correct. Yes. So something that I've left off, I suppose, on my slides is that, yes, we can, of course, constrain the metallicity of the atmosphere. We use a free chemistry, so that's not going to be tied to a solar ratio, but you can make an argument. You can estimate the metallicity from a mean molecular weight. They tend to be quite high. But again, the reason I hesitate to give you a good answer now is because the metallicity and the surface gravity are often quite degenerate in our models. And so if I'm retrieving a surface gravity that is not unphysically, but at least implausibly high, then I also do not trust the metallicity. And I think it has something to do with the way that we're retrieving the structure of the atmosphere. That depends on the assumptions that we're making in our model. So you're absolutely right. These retrieval codes will give you a constraint on the metallicity. I just can't give you a good number right now. I think it will take JWST or to see whether we can get a better constraint on the structure of the atmosphere, which will then, as a byproduct, hopefully yield more accurate constraint, at least from our assumptions about what these atmospheres should have.
Mm-hmm. I think you mentioned that the physical structure of your atmosphere is actually not physically consistent with this radiative convective model.
Mm-hmm. Mm-hmm.
If you constrain the physical structure to be physically consistent with such a model, could you find a solution that maybe a slightly worse fit, mm-hmm. but it's still reasonable?
Yes, so people do fitting with radiative convective equilibrium kind of, or a more constrained thermal profile that follows the structure of a radiative convective profile. I have not done that, but others have, and you can find a solution for atmosphere. I can't quote for you exactly what you would find, whether it would resolve the gravity questions. I don't think that I think it introduces different problems. I think you do have some problems with limiting yourself to that. So I can't give you a good answer about what you would expect, but yes, other people have adopted more restrictive parameterizations, and I can't recall what they. I think most of the retrievals that people have been working on have allowed for either a more free temperature pressure profile or something more, something freer. In order to fit some of the features. I think that you lose some of the accuracy if you make that that restrictive of an assumption. And something I didn't go into is that there are hypotheses for why we don't see a radiative convective structure in the atmosphere, even if what we retrieve may not be, immediately plausible. So,
I guess the short answer is you get much worse fit if you fix the temperature profile to a radiative convective equilibrium. And I think the TP profile also you showed is is a cloudless model. And for those models, if you compare it to the early L dwarf, the model spectrum looks nothing like the observed spectrum. You really need to put a lot of clouds into those models to make them at least resemble the color, the observed color.
Yeah. So that's a good.
And I'm kind of interested to see if you actually use the cloudy radiative convective equilibrium model, compare their TP profile to your retrieved TP profile, what that comparison would look like. That would be, I think, a much interest. I would say that's probably I would be more interested in that comparison. So I have a few questions, a few about retrieval, a few probably about more wider picture questions. For retrieval, I think it's really exciting to mention about this comparative working group, compare different retrieval framework. I think it would be helpful if you could introduce to this group what are the possible differences between all those retrieval code that give different answers. Are those the opacities or the treatment of the temperature profile or treatment of cloud? Or what are these differences?
Oh yeah, that's a wonderful question, and yeah, I there's many little details that are ideas here that I had to gloss over, but this is a good point. So I suppose you could divide the differences in models into two camps, right, or two categories. One could be you're actually parameterizing or applying a different model of, say, the temperature pressure profile from one model to the next. And so it wouldn't be surprising if you, say, retrieve different results. There could be similarities, but that would be one category of difference. But as you pointed out, you found the opacities, and in fact, there have been other working groups prior to within the cuisines group that have been just focusing on radiative transfer comparisons. So I think really the efforts right now are to see how the fine-grained assumptions about just the input data of the physics, like the opacities, right, that we use for each molecule and those sorts of things, how codes differ at that level. I think that's kind of been the main thrust of the retrievals to this point. Or excuse me, I should say those were for forward models. So those were not retrieving on any data. They were just showing, okay, if you make the assumption of, a basic target at this temperature and this, this sort of thing, what does your model produce for a spectrum, and how does that compare with the other, 4 models that they're testing? So it really, I think at this point, it really is down to, the input, physics and that sort of stuff.
Yeah, so I think beyond that, so retrieval became this kind of a prevalent methodology of us trying to understand what the composition of a planetary atmosphere. I was wondering about do you have the knowledge of this extend beyond the study of a planetary atmosphere? The reason I'm asking is at Virginia, we have the largest group trying to understand the C2O ratio in protoplanetary disk. Do you see any of this kind of method that can be applied beyond the planetary atmosphere?
I suppose I haven't, I suppose if you're looking at the emission profile of a protoplanetary disk and you're able to get data from that, I suppose you could certainly write a similar code or adapt this to retrieve the chemical properties of that. I just haven't considered that. I would be certainly interested in hearing more about that, or investigating that further. Maybe others have.
The differences are probably mainly in what are the important physics in this two type of astrophysical environment, right? The chemical reaction rates are much more different. The time scales are different.
I see.
Radiative transfer like the physics are the same, but you're dealing with different different type of opacities, atmospheres. So
Right.
I have no idea like whether this has been applied. I've heard from some people talking about it, but I would definitely think this.
Well, here you're in chemical equilibrium, we think, right, in your atmosphere. So it's different. It's quite a different setup. Whereas the disk,
Right.
maybe the inner disk would be approach.
But I guess you can set it up in a way that can mimic the protoplanetary disk atmospheric environment. But I don't study it myself, so I just want to have some knowledge from Arthur about it.
Yeah, my questions were whether we could, like as Jonathan alluded to, whether we could separate the if you could spatially resolve like certain radial, like here's a profile of the disk at this distance versus the inner disk, outer disk, and you expect some chemical stratification, that would be my first question. I don't know, at least in the infrared, and then as follow up, right, the chemical timescales. I will say that our philosophy in a lot of, I don't call it philosophy, that's a bit generous, but is at least my approach so far is to use the physics that are appropriate, but a lot of things that we leave free in the assumptions, right? So for example, the TP profile is just a series of nodes that we connect, right? So what the question of the timescales, I'm wondering if like that sort of approach is, characterize the data and then what the structure of the data, and then try to interpret that in terms of like a model assumptions or that sort of thing.
I was going to ask about the stellar evolution side.
Mm-hmm.
Are you fitting an age? Some people in our group work on fitting pre-main sequence tracks to
Mm-hmm.
stars and low mass stars.
Mm-hmm.
Do you have any? Are you working even in that context? Are your models part of stellar evolution? Do you have an age of the system fit from your models or not?
No, not at all. So my model only fits the photospheric structure of the companion.
Right. But
so these are
to somebody like a Baraf model or something.
Mm-hmm. Yeah. So yeah, you of course could compare with models of stellar, substellar evolutionary tracks and just see how that compares. And so I think that's what before the original paper kind of compared on like a luminosity, and there were a couple of gravity indicators. So up until we started working on it, that's where we got the estimates of the age and the gravity from the target. But I have done no work in that field, or have done those comparisons. At least in this paper, we did not directly do those comparisons. We just relied on the literature. But that is a very important question. So it's certainly something worth looking into.
Right. So I'm just trying to think what it means. So if you fix the age, of course, these tracks have a lot of uncertainties themselves. Mm-hmm. But if you do think it formed a certain time ago, then it places some constraint on the mass, which you seem to be struggling with the mass, maybe.
Mm-hmm. Yeah, and this is not you're pointing to a thing that we so Michael Meyer, who was my supervisor at University of Michigan, often said this. It's like, well, just we have a constraint of the mass from these evolutionary models. Why not simply impose a prior that is corresponds to the radius and the gravity that would give you or a gravity that would give you an appropriate mass constraint from those that would like a Gaussian prior on that. And the answer is you could certainly do that, and so the results I show here are not a result of that. We have done that in the past. What I believe, so that is certainly something that factors into our current retrievals. So we're kind of doing a free gravity retrieval and then a one that's tied to existing mass priors. The issue that we had was that here's a way that I'll frame it. And Ryan and I have talked about this a little bit, Ryan McDonald, who's currently in Michigan. And the way that we look at the atmospheric characterization is when we get these kind of physically implausible results from letting the model be too broad, say, have a gravity prior that's just, wide open. It's interesting and possibly informative to see what happens when the model fails. Does it, in this case, does the model, when we give it a free gravity, does the surface gravity, because when we impose a prior in the past, what would happen is that the gravity would often push up against the upper edge of the prior if we had like a cutoff in the prior for these models. And so that was a persistent feature of each of the models that we ran. And so, what I ended up settling on was I'm going to allow the priors to be broad, and I'm going to allow the model to give me a wrong answer. And my question was, does it simply continue off into infinity, or as far as I can set the bound to, or does it stop somewhere? And the answer is it always stops somewhere. And in that case, for the one that I showed you with this 2 mass, it stopped around log G of 6. And so I know that that's not probably, at least probably is not what's going on in these atmospheres. But for me as a person who's studying atmospheric structure, it's interesting that it's finding a solution that says, okay, whatever photosphere that I'm trying to constrain is the best fit that I can get is by essentially just kind of accordion squeezing the atmosphere to a very high surface gravity, higher than we expect it, so that I can get the opacity profile that you want from me. And sorry,
maybe it's time to bring back some of those constraints. And
yes, right. So I completely agree with you. Sorry, and I went off on a little tangent, but the idea, I guess the philosophy that I was coming from was that in the midst of data that are not telling us a complete picture, I am interested in the way that the model fails, and and then that could tell us something about the future. But of course, when we get when we move to the future and we get these, or JWST even in the present, we should not forget the priors. Absolutely. So sorry for going off a little longer.
No, that's fine. We have 5 minutes left. We focus mostly on this system, of course, but I don't know if you wanted to expand a little bit to the super Earths, sub-Neptunes, or even Earth and Venus, if there's a point you want to emphasize that relates here.
I do have a question about it. So for the Earth-Venus dichotomy, when we speak about that, the system is thinking about the TRAPPIST-1. So there is, I guess there's new like 70 hours of JWST time approved trying to catch atmosphere of TRAPPIST-1e. Do you think like the modeling work you're working on, like trying to differentiate like exo-Earth and exo-Venus, can give us some insight of what can we tell, like if we observe like a 1 point spectrum or like 1 photometer of a TRAPPIST-1 planet, can we tell it's exo-Earth or is exo-Venus?
It's a really good question. I will hesitate because the amount of work that I've done in directly trying to model exo-Earths and exo-Venuses is actually quite limited. So I don't have a lot of background to rely on. But I understand, and I'm also interested in the questions that, allow us to probe those atmospheres and try to figure out, is there this dichotomy that we see in these atmospheres? So I don't know if I can give you a good answer as to, what I expect to see, only that I think that the reason that I brought up these kind of 3 dichotomies is more that I think I see in the discussion about the framing of terrestrial planets as either something that's habitable, that is, it falls in the Earth camp, or something that is completely uninhabitable on the opposite end, that falls in these Venus camps. Are we going to see the strong split that may be due to some sort of atmospheric evolution over time that is that, you know, if Venus, say, as some people believe, that Venus was more habitable or hospitable in the past, in its distant past, and then only after some 500 million years or billion years or some time frame evolved to the state that we see it today. What does that, I think that I don't know what to expect from the TRAPPIST-1 system other than, you know, what we already know. And I'm not sure, like, framing it as this kind of one or the other is a good way to start asking the question, but I don't know where. I think we're going to see a lot more of a messy picture that have to stitch together. Okay, what are we seeing? Is it the result of all these different, you know, evolutionary processes and different states that are very not similar to the Earth and that sort of stuff? So I completely didn't answer your question, but I think it's just, I don't know what to expect, other than I think people are interested in the question of
profile.
You know,
because Venus is hotter. Is that what someone would look for?
So you said
As an issue with
70 hours of James Webb is on this system. So what exactly is involved? Do you know the details?
spectrum?
Trying to observe a spectrum of TRAPPIST-1e.
Mhm.
There's only one program which recently approved. I think in total probably there are, I would say, 300 hours of JWST spending on the TRAPPIST-1, just one star. So there will be a lot of data. So this new program, I can just talk a little bit about this new program. I'm no part of it, but I see the abstract. It's trying to just trying to probe whether TRAPPIST-1e, which is one planet in the habitable zone of TRAPPIST-1, has atmosphere or not using transmission spectroscopy. So the problem we have seen before to observe the TRAPPIST-1 planet spectrum is the star is very active. So the star is doing a lot of contamination to the spectrum of the transmission spectrum of any planet. And the new knowledge we learned from previous GMC observation is the innermost planet, TRAPPIST-1b, is airless. There's no atmosphere. So they think they can use the TRAPPIST-1b as a template to correct for the stellar atmosphere. So they're proposing to observe double transit of B ahead of E. So observe one transit of B and right ahead of the transit of E. Then they can use the spectrum of B to get rid of the stellar part, and then any feature they see in the transit of E should be part of the atmosphere of that planet.
Interesting.
Yeah.
Yeah, they're going to observe 5 of these double transit events to probe the atmosphere on the TRAPPIST-1e. And this is like the planet in the habitable zone of TRAPPIST-1. So that's why I come up with this question: can we get any idea of what its atmosphere is like if we get a 3 sigma detection of its atmosphere?
Yeah, and I think the answer is you probably will learn something about the atmospheres if they are there. I just at least in terms of this framing, I'm not sure whether you'll see something like a clear split between things that look, you know, very much like Venus versus Earth. I just don't know what to expect. But that, you know, the one thing that your discussion, Yifan, brought, or your point brought up, is that we're talking about getting the CDO ratios, and one thing that came up recently outside of this discussion is using an atmospheric model like ours to characterize the primary, because TRAPPIST-1 is so low mass and so, you know, low temperature that it actually kind of maybe in the realm of something that we could easily do with our existing code. So I thought that would be interesting. Can you do an independent characterization of the host? And, you know, we're using a one-dimensional model here. So if it's an active system, you know, with a lot of, you know, highly variable, then you expect it'll probably fail to capture all the features. But, you know, that could at least be a starting point for like a, you know, if we build a variability model, could we run it by TRAPPIST-1? That's an interesting question that I'm thinking about.
I think people probably are doing that. There's
Yeah.
also approved that
Yeah.
like archival program to
Yeah.
try to categorize the stellar spectrum.
Yeah.
Something similar. It's not like restricted to TRAPPIST-1. It's to pretty much like all the planet host stars that has been observed by JWST.
Yeah,
Great.
no, that makes perfect sense.
We're at the hour now, so we should wrap up. But that was great. Thank you very much, Arthur, for the great discussion. We look forward to seeing you in person in Charlottesville.
Yeah. Thanks for asking very good questions. I think there's a lot of opportunities.
Arthur has to get up really early in the West Coast.